Hello, my name is Ryan Wittleder, and welcome to my AE 1601 glider project report. This project tasks us with designing, building, and testing a glider made primarily from balsa wood supplied to us at the start of the semester. The glider would need to fly at least 20 feet horizontally after being thrown by hand, and it would need to fit within a 16 by 16 inch box, shown here. Also, it would need to hold together for the duration of the test flight. To me, success in each of the project requirements was measured by far exceeding the minimums while retaining the most simplistic and efficient design. For example, I knew from the start that I wanted to double the minimum flight distance in my testing, and I knew that I needed to capitalize on stability and precise knowledge of the balancing of my aircraft. Through several design iterations and repeated testing, I feel as though I have been able to actualize my visions for the design project and produce a successful output. My initial design was quite complicated, with the dimensions almost arbitrarily laid out. I initially planned to make my glider a foot in total length. I planned to cut the supplied dowel of length 2 feet into two pieces of equal length. I then planned to stack the two pieces on top of each other and sand the topmost piece to create a camber of sorts. To add weight to the forward portion of the aircraft, I planned to 3D print a nose cone. With regard to wing design, I initially set out to create a slightly swept back wing design, reminiscent of the wing design found on most commercial aircraft. The total wingspan of my first iteration was 14.5 inches, and the total wing area was 37.6 square inches. Thus, the aspect ratio was a mere 5.588. Much like the design of the wing, I planned to make the aft horizontal stabilizers with a slightly swept back design. For the vertical tail, I planned to make a configuration similar to the shape of a shark fin, with a base of length 2 inches and a height of 2 inches. I ultimately ended up scrapping this design entirely due to the low aspect ratio of the wings, lowering the lift-to-drag ratio, and the sheer complexity. The major design alternatives I considered centered around three central areas: materials, specifically at the nose, wing shape, and adhesive used. With regard to materials, I initially deliberated between using 3D printed components and extra wood at the bow to create longitudinal stability. After revising my design, I was able to settle on a plastic nose cone. All three materials presented their own balancing issues, and each moved the center of gravity to different locations along the fuselage. With regard to wing shape, I was torn between two central designs: a swept-back wing versus a rectangular wing with trapezoidal ends. The former would provide greater initial airspeed, but it would also have a much lower aspect ratio and much less lift generation. The latter would cause increases in the lift-to-drag ratio due to the higher aspect ratio, but test flights would now be contingent primarily on the functionality of the wing structure as opposed to my ability to forcefully throw the glider. With regard to adhesives, I debated between using twist ties and CA glue to hold the wing structure down. The former would allow me to freely move the wing structure at my leisure while also keeping the wings relatively snug against the fuselage, but the twist ties would begin to loosen and lose their stability after several test flights. The CA glue ensured that my wings were fit securely to the fuselage, but it prevented any last-minute movement of the wings after they were glued on. Thus, I could not make any adjustments for balancing purposes. Here's a table of the different wing structures I tested, which served as one of the primary design iterations I made to my craft. We'll come back to this table later, but for now we'll focus on iteration B. This was the first iteration for which I created a physical product, and it was used in the first test flight. Test Flight 1 laid the groundwork for achieving the design I wanted, but it was clear to see that improvements would need to be made to ensure that I was reaching my self-imposed standards. For this test flight, I utilized the Iteration B wing structure from the previous table and images, and I used a sanded camber to add extra weight to the bow of the aircraft in order to maintain stability. Here's a video of me flying the craft inside the Colk. As one can see, it continually pitched upwards as a result of the lack of longitudinal balancing. In my other trials, the glider also rolled left quite frequently, due to both imbalances in my wing structure and the weak nature of the adhesive tape I used to hold the glider together. From here, I knew I needed to better balance my glider in future test flights. I knew I did not want to return to the 3D printed design I conceptualized earlier, but I needed a component that would move the CG of the aircraft to about 2/3 of the way up the stern. Thus, I settled on a plastic nose cone supplied to us in the rocket project, conducted earlier in the semester. With a mass of approximately 7.23 grams, this component easily achieved my desired outcome. As a result of adding the rocket nose, the craft's CG moved to about 6.5 inches from the bow down the fuselage. I attached my wings quarter cord directly in front of this point in an attempt to generate as much lift as possible. The other major design change I made regarded the wing structure itself. In design iteration C, I lengthened the wingspan from 12 inches to 15 inches, decreased the root chord width from 1.5 to 1.25 inches, and also decreased the tip chord width from 0.875 to 0.625 inches. The primary purpose of these changes was to increase the aspect ratio of my wing structure. This, in turn, increases the lift-to-drag ratio and extends the duration of my flight. Test Flight 2 is radically different from Test Flight 1 in terms of vertical and horizontal stability. The glider flew much further with the new wing, and the plastic nose cone helped keep the glider at a controlled angle of attack. I used the twist ties for the first two tests, which became increasingly unstable over time. I thus glued the wing down after, and my results improved drastically. Here are the final dimensions of my design. Once the design was complete, I calculated the coefficient of lift by using the angle of attack from Test Flight 2. I used the software tracker to analyze the motion of the glider with respect to a parallel flight path, and I multiplied the resulting angle by 2 pi to obtain the coefficient of lift. My craft's angle of attack was approximately 3.4 degrees, or 0.373 radians, in this test flight. To calculate the coefficient of drag, I used the following relationship. My glider's coefficient of drag was approximately 0.022. On fly-off day, my glider design proved to be overwhelmingly successful. My first throw was my glider's single longest glide distance, but the second throw saw the glider roll and yaw to the left. The wind and the nature of my throw likely influenced this. In summary, I was able to surpass many of the standards I laid out for myself. If I could repeat the project, however, I would likely have elaborated further on the wing design. My roommate, Nicholas Gao, created an airfoil of sorts by stacking the two wing templates atop each other and sanding down the topmost piece. This would likely have increased my lift generation drastically through the creation of pressure gradients under the wing.